Hello again, everybody. Thank you for joining this webinar. We are expecting a few more people to come on, but we'll get started. They can join when they join. We've had actually quite a lot of people have asked if we're recording this session, which we are doing. So again, the recording will be going out to people probably in the next day or so. I'd say this webinar is all about EnergiVault and the new product that we've developed here at Organic Heat Exchangers. Just a couple of admin points before we get going. All the attendees, you're all automatically muted and your videos are switched off, so nobody else can hear or see what you're doing. As just mentioned, we are recording this. We're planning to take 45 minutes to go through the whole webinar, but we certainly will not go over the hour if it does go on a little bit. As we're using Teams for the first time for this webinar, if you want to raise questions, if you could use the Q&A facility that should be shown at the top of your screen, just depending how you've got Teams configured. There is a chat and the Q&A facility, but if you go use the Q&A session, if you've got any questions, that would be really helpful. Just to kick off, I'm David Grundy. I'm one of the directors at Organic Heat Exchangers, and I'll be leading us through the webinar. We were due to have two speakers, Bob Long and Jeff Barker. Bob, unfortunately, is waylaid unavoidably and can't join us, so Jeff is going to be doing the bulk of the presentation today. So perhaps, Jeff, can you just give everybody a couple of minutes on yourself, please, as an introduction?
Sure, yeah. As Dave said, I'm Jeff Barker. I'm also Director of Organic Heat Exchangers. By background, I'm a mechanical engineer. Spent probably about 30 years involved with energy-related startups, usually demand management, so everything from micro combined heat and power to voltage optimization, energy storage of other types as well, including compressed air. So, and also been involved in a business which set up an energy supply company. So, very much involved over the years with a lot of different energy-related activities, technology development, and energy management activities. So I've been involved with David and Bob, who's not joining us today, for the last 3 or 4 years on OHX. So today I'll take you through sort of a Q&A type approach between David and I. David will sort of ask questions, and we'll basically address many of the key points that people ask, or we know people ask of EnergiVault, and present some of the information which will help you take away a better understanding of what it is and what it can do in different applications.
Yeah. Thanks, Jeff. And I guess just to kick off, it's World Refrigeration Day today, which we've agreed we're a sponsor of. And the topic for World Refrigeration Day this year is next generation cooling. I guess just to start off, Jeff, everybody will be used to traditional chiller systems that provide cooling on demand. I'm going to pull up a picture of EnergiVault, but can you perhaps just explain to people what EnergiVault is and how it's changing this traditional system?
For sure, yeah. I mean, I think most people on the call, probably because you're on the call, I guess you're either practitioners or interested in some way in energy storage and cold energy storage. I mean, chiller systems have been around for quite a number of years, as most people know. Probably from the 40s onwards, there was a small amount of cold storage, usually solid ice systems. But again, I think as David alluded to, most systems are demand led. So, if you need that cooling, the chillers come on in varying degrees to deliver a set point, depending on the application, whether it be for air conditioning 12 degrees, or whether it be a cold store or a freezing cold store minus 18 degrees. So depending on the application, the chillers obviously come on to deliver that demand. Over the last 60, 70 years, there have been the application of cold storage using solid ice systems. Again, people may be familiar with some of them. We've lost the image, David. I don't know whether you were trying to change.
Yeah, so I'll take it down, Jeff, just while you're talking. I'll bring it back up again.
That's
you want to explain.
Yeah, you can bring the diagram, the schematic up actually as well. So yeah, most people may be familiar with ice storage as it's been deployed typically on dairy farms and elsewhere, where there's short duration peak cooling requirements, often in the case of dairy farms at the end of a bit of a wet string of supply cable, so perhaps isn't the the capability to deliver high cooling based on the electrical connection. So ice storage has been around for a while. It's pretty rudimentary in most cases. It's basically building a solid block of ice in a tank around a series of coiled copper pipes, either by direct expansion or by glycol. So effectively, those sorts of systems are relatively inefficient when they charge. You're growing an insulating layer of ice around a cold source. And when you're discharging it, effectively you're discharging a solid block of ice as well. It makes it much more difficult to discharge at high levels and high rates of good cooling. So basically, you have no flexibility in the way that you use that store. That energy store doesn't give you a great deal of flexibility in how you apply it to a cooling system, to a chilled water system. So that has been one of the major constraints for cold energy storage for quite some time now. But EnergiVault is changing that. EnergiVault basically is a system that produces that same latent stored energy, but in billions of tiny ice particles. So, and as probably people will be familiar, you have your ice in your gin and tonic. By the time you've finished it, if you're thirsty, the ice will still be there. If you have a child's slush puppy, which is perhaps a similar analogy, then that will chill down the fluid very much more rapidly because the surface area is so much greater.
So just interrupt there. So EnergiVault is storing cold energy as an ice slurry. We'll come back to the ice slurry, but can you just explain to people how EnergiVault actually integrates into an existing system?
Sure.
I'll put up an image here that I think will help.
Bring up the sketch, the schematic. So EnergiVault is typically applied in a system which has a chilled water circuit. So on the right here, you'll see, what might be a typical system. In this case, as shown as cooling an office block, but it could be a hotel, could be a food factory, could be a brewery, could be a data center, anywhere that has a chilled water circuit. And typically, the EnergiVault system will be connected into that via what we simply refer to as the interface heat exchanger. So you effectively decoupling the EnergiVault system from the glycol-based chilled water circuit, the existing circuit. That allows a couple of things. It allows us to tune the fluid on the left-hand side, the EnergiVault fluid, and again, it's a glycol-based solution, but we can tune the crystallization temperature to optimize the system. So the EnergiVault effectively comprises of three main elements. If you sort of ignore the cooling towers as a fundamental part of the refrigeration, a thermal battery, which is a volume which contains the ice slurry, the latent energy, a thermal battery charger, which is primary refrigeration plant. In the current case, it's an ammonia system, and an EnergiVault smart gateway, which basically provides the interface for control both to external cloud-based optimizers, which are our developments in the EnergiVault platform, and also connecting to the client's BMS, which is still dominant in terms of how things are controlled, but we'll come on to that later. So essentially, you've got a store, a charger, and a smart intelligent control element connected via a heat exchanger to the system.
Yeah, Jeff, I've just pulled up the image of the actual demonstration unit here.
Yeah.
So just want to explain what the two parts of this are.
Yeah, so what you're looking at here actually is our first installation at a pharmaceutical plant up in Northumberland in the UK. Not knowing quite where everybody's from on the webinar, but this is basically in the northeast of the UK, north of Newcastle. And the system comprises of the charger, which is on the right-hand side in the container, the store on the left-hand side, and obviously the controls element is actually a box in the boiler room, which is out of shot to the right here. So effectively the system is modularized. The charger is in a 12-foot standard ISO container, and the store is in a 20-foot standard ISO container. So very much a modular design. You can mix and match a little bit. The charger is typically 50 to 60 kilowatts refrigeration, and they store nominally up to about a megawatt hour of thermal storage, depending really on obviously the duration in which you charge the system. So in this particular configuration, you could charge it for 20 hours to get a megawatt hour, or you could have 2 chargers in a similar system and charge it in 10 hours. So quite a modular system, and basically producing a considerable amount of daily available cold energy to optimize existing systems.
Yeah, Jeff, you mentioned earlier that we're storing energy as ice slurry, or liquid ice, as some people call it.
Yeah.
This is probably quite a new concept to people. Can you just explain a bit more about what ice slurry is, and how it's made and why it's so efficient?
Okay, well, in the photograph that you saw on the right-hand side there, the charger comprises mostly conventional refrigeration components that people in the industry will be familiar with the exception of the crystallizers, which are actually the evaporators within the refrigeration system. And there are 4, which is probably what you saw, those 4 individual upright pipeworks. So you're going to pull that up again, David. Yeah, so on the right there, you've got the 4 cylindrical elements at the bottom are the end caps of the crystallizers, the evaporators effectively. And you essentially recirculating the fluid from the tank through those crystallizers to produce this fine crystalline, some people refer to it as binary ice, a very fine crystalline solution of about 60% solids to 30%, or 2/3 to 1/3 solids to liquid. And basically what you have is a maybe 2-3 or 0.2-0.3 millimeter small spheres of ice surrounded by the glycol material. So they don't actually bind together, which is one of the key things here. So you've got quite high density latent heat stored in the ice particles, but you've also got the ability to have the fluid to move around them, which is a key part of being able to provide a very, very rapid discharge or release of that latent energy. And this is where EnergiVault sort of changes the game a little bit from solid ice systems that we refer to, such as those used in dairy farms, where you can charge the system at a relatively low rate, let's say 50 kilowatts. But once you have that stored energy, you could discharge it possibly in 30 minutes or an hour. So you can discharge it at rates of, well, we've been demonstrating it up to 200 kilowatts, for example, but we know we can do it higher than that. So where applications require short-term peak loads, where there is a need to optimize existing chillers, avoid say a cascade of chillers, avoid part-loaded chillers coming on to improve efficiency. There are many applications of this, of course, but effectively that ability to discharge very, very rapidly gives you incredible flexibility with how you use the stored energy, which has not been possible with conventional ice storage so far.
Okay, and just going back to the charger, Jeff, I think you described it as a fairly standard refrigeration chiller system. Mm-hmm. It uses ammonia. Can you just perhaps explain to people why we're using ammonia as opposed to any other refrigerant?
Well, a number of reasons. It's certainly an efficient refrigerant to use from a coefficient of performance point of view. It also has obviously a low global warming potential and is quite effective from that point of view from a CO2 point of view. So so ammonia is a very efficient refrigerant for the application that we're putting it to. In this particular case, we're typically evaporating at around about -10. And we're creating an ice slurry at about -3 degrees. So in this particular application, where the duty on the demonstration unit, which I mentioned at the pharmaceutical plant, basically has a set point around about 12 degrees. So that chilled water is effectively used in air conditioning pharmaceutical laboratories. So in that case, we are storing that latent heat, that latent energy at -3 degrees. And the ammonia suits that particular application very well, and as I say, it's got low GWP.
Okay, so we're using a standard refrigeration system to produce the ice slurry or the binary ice in the crystallizers, and that then gets stored in the tank, which is on the left-hand side
Yeah,
of the
and
picture we showed
I
earlier.
mean, without going into too much detail and disclosing sort of too much of the intellectual property, the system is a flooded system. So effectively, what that means is the evaporators are flooded, and it gives us an ability to control that crystallization temperature really quite accurately. And in doing so, again, it addresses previous problems that people may have come across with the types of heat exchangers we're using. So we're overcoming quite a few issues and problems in past technology by having the system that we've got and having a flooded system, which again is used in other applications, but it's in particular in this case, it again is very suitable for having a good control of the evaporating temperature and therefore the stored temperature of the energy that we're storing.
Okay, and you said earlier that the store is a megawatt hour.
Yeah.
In the standard size. So how quickly can that be discharged?
Well, I say we've demonstrated it. It's discharging it at 200 kilowatts. So if you have that megawatt, you've got 5 hours of storage, 5 hours of usage. We believe we could probably discharge it in considerably higher rates than that, up to indeed maybe up to a megawatt. So potentially that 1 megawatt hour could provide support for 1 hour. So it is very flexible in that regard, and the tests we've done so far suggest that that's certainly the case.
Okay, and you mentioned earlier that these are very modular. So if you needed, say, 2 megawatt hours or 3 megawatt hours, it's pretty straightforward just to build these up.
Absolutely, yeah. I mean, in many ways, the storage element is actually the easiest part, the less complex part, shall we say? It's a store. It has particular features inside it in order to distribute the flow and returning cooling water into the tank, but it's not overly complex. The more complex part is the charger element, which is the refrigeration plants and crystallizers. But similarly, it's been designed as a modular approach so that we can, obviously applications vary considerably. The companies that we've been speaking to, as you know, David, range from data centers to, breweries, food producers, pharmaceutical companies. And so the size and scale of the systems, vary depending upon, the nature of the client site. One example is one extreme, you might say, an extreme payback situation where a company has significant problems at certain times of the year where they simply can't meet the cooling demands that their already quite considerable chiller plant has. And actually the way they solve that problem is to deliver more cooling to the cooling towers. And so EnergiVault in this case is being considered for that application, where the payback is, well, we were told days, because during that period, the operating plant that this chiller system is connected to actually cannot deliver the product to the quality that's required, and so that is millions of pounds a day. So there are quite a wide range of applications, but yeah, fundamentally it's a modular system, and you can use it depending on the scale of the site you have. And one thing that Bob often says to people is, it's not a case of you have to fit one particular size of system to your plant. Whichever site, in other words, you can start with a smaller system, and even if your demand could utilize 3 or 4 megawatt hours of storage, starting with 1 megawatt hour of storage is still a good place to be, because you're still pro rata getting the same benefits. And of course, it's often a good way of introducing something that's new to a site as well, by starting and scaling up from a demonstration of that technology.
Okay, and in terms of how the system's controlled, you've explained the charger, you explained the store and the smart gateway, but how is everything controlled? How does it run in practice day to day?
I mean, there is a slide, David. I think at the end, I've got a blank screen in front of me, so I'm not sure whether you've got have you got a slide you're trying to put up there? Okay, yeah. Do you want to go back to the previous one? I think there's two related. That maybe not that one. Sorry.
No, that's
yeah. If you go back to that one, yeah. So the basic way which we anticipate this to being sort of installed and controlled in most applications, or controlled, is by connecting the EnergiVault gateway to the on-site billing management system. And in the case of the Quotient demonstration system that we showed in the photograph before, that's exactly how we operate this. So effectively what we're doing is connecting our own control module to the BMS and taking instructions from that. Now, that can be set up in probably one of several ways. One, where there are more than one chillers on the site, effectively what we can do is the BMS treats the EnergiVault thermal battery as a chiller with a certain capacity. So it can say, okay, we'll set EnergiVault to be chiller 3, let's say on a 2 chiller system. So in other words, when the main chillers aren't or unable to deliver the demand, then EnergiVault comes in and supports that demand as effectively the 3rd chiller. On the other hand, the system can be set up so EnergiVault is the primary chiller. And in fact, we've done that in some tests recently by basically, because at the early part of the year, then the demand was relatively low, there was actually a relatively sort of modest demand, which allowed EnergiVault to satisfy all of the demand for several hours. So in that case, the BMS sees or is controlled and sees the EnergiVault as the primary chiller number 1. So effectively, you're basically using the BMS to determine what sequence of chiller capacity is brought online, and whether it be the primary chillers or whether it be EnergiVault, and you can mix and match when that comes on. Similarly, you can do that by the BMS again setting the temperature which it wants each of those chiller elements to come on. So fundamentally, you're connecting the EnergiVault to the existing BMS, and the BMS remains in control of the overall chiller plant, but it knows what the available capacity in EnergiVault is, and it can determine when and how it deploys it. Now, throughout the year, there may be, well, in fact, there are different priorities. So again, using the Quotient example, at the early part of the year when the demand is lower, because obviously the ambient conditions are not as hot, then you might see EnergiVault as the primary chiller more often than not, because it can operate at least for 3 or 4 hours, and therefore it could be operated as a primary chiller between 4 o'clock and 7 o'clock, for example, thereby avoiding the high cost GEOS charges, distribution charges in the UK. During the summer, it may be that it's set up as the support chiller number 3, so it effectively ensures that the maximum or the demand is met, and that acts as a support chiller. So throughout the year, the BMS can configure it and set it up in a different way to deliver the optimum performance and optimum savings. So
Okay.
effectively it connects to a local BMS. A long answer to a short question.
Okay, and so you mentioned earlier that you can only see a blank screen with me. I've just realised my camera's malfunctioning, so that's a tech problem at my end. So apologies to everybody for that. So I'll try and keep my amounts of talking to a minimum, and then I'll switch back to you. A lot of what you talked about there, Jeff, is really take us into the area though of economic returns and carbon savings, etc.
Yes, yeah.
Can you perhaps just talk us through how EnergiVault can be used to unlock value? And I'm going to pull up another slide here for you.
Yeah. Okay. I mean, what we've found talking to a lot of potential clients is carbon savings actually one of the main drivers, but obviously energy saving and cost saving, particularly over the recent past with energy costs being so high, is not surprisingly equally important. Just to sort of explain a little bit about where CO2 savings come from. One of the main applications for EnergiVault is the optimization of existing chillers. So chillers, when they're on part load, are generally not as efficient, not operating as efficiently as they are on full load, and depending on how you set the controls up, effectively you can avoid that, depending on how many chillers there are and whether they're cascaded or whatever. So you can effectively reduce or replace that inefficient chiller capacity, and we found chillers in sort of February, March time running at with a COP much less than 2. If you can replace that with stored energy, which has been created with a COP over 3, then you're effectively roughly 50% more efficient delivering EnergiVault instead of that part-loaded chiller. If you're 50% using 50% less energy, then correspondingly you're using less carbon, and depending on where you're taking your power from, whether it be local on-site generation or mains grid, again you'll probably reduce your CO2 by at least 50% when you're replacing that chiller load. So there is a period of time when you're optimizing chillers that you're effectively reducing your CO2 by improving the efficiency of the energy which you're producing. One of the other big benefits of EnergiVault is that if a site has on-site renewables, in particular, PV on the factory roof or whatever, or a small wind turbine, but not only is it less cost effective if you're exporting that on-site generation, but obviously if you're able to optimize and use that energy to store energy in an EnergiVault, then effectively you're maximizing your zero carbon energy, and thereby obviously delivering quite a significant saving. And what we're finding is that customers that may have had excess PV and not seeing all the benefit of that PV because they're exporting some of it, you can ensure that more, if not all, of that on-site power is then absorbed into the EnergiVault battery. So again, that's another element of where CO2 savings can come from. Most people perhaps are aware that the carbon intensity on the grid varies between the night and day, not as much as it used to. It used to be quite a significant variation, but there is still variations in the grid carbon intensity, and again, depending on the time and duration of charging the EnergiVault, if you're discharging it at a particularly high carbon intensity period, which is typically between sort of 4 and 7 o'clock in the day, when the marginal plant is coming on and the carbon intensity gets greater, then again, there's another area where you're saving carbon. So there's several areas in which you can demonstrate carbon emission saving. From a sort of more conventional savings, pounds, shillings and pence, obviously an energy store allows you to load shift. And depending on, again, there's so many variables in this, depending on customers' situations. But if you're a customer with a day-night rate, let's say, on your electricity, and then by charging during the night and shifting that expensive daytime energy with nighttime energy or off-peak energy, then clearly you're able to demonstrate a saving. Also, you can optimize that saving by minimizing not only or avoiding the high tariff energy, but also avoiding the high GEOS costs, which are the distribution charges, which are typically charged between 4 and 7 o'clock. So load shifting is clearly a large area of value. In addition to that, in fact, more and more prevalent these days is the demand response value that can be obtained from National Grid ESO, often via an aggregator. But actually last winter, there was a new system introduced. In fact, some people on the call may be familiar with it because it was actually targeted initially at consumers. It's called the Demand Flexibility Service. And that basically paid consumers £3 a kilowatt hour for shifting energy from those peak periods, and did that by a day ahead, informing the customer of an event, which may have been an hour or 2 hours. Typically, it was between 4 o'clock and 7 o'clock, often between 5 and 6. And if you take an example of the system we have at Quotient, that 1 megawatt hour, if it was discharged in those 22 periods during the winter that were part of the demand response program, then that would have created £26,000 worth of value. So demand response is becoming an ever more valuable element. So in other words, you could say that's in front of the meter value, network value that you could gain from energy storage, in addition to the behind the meter value, such as the shifting of the optimizing of chillers, which not only is carbon efficient, obviously is energy efficient, pounds efficient, and the baseline, the time of use shifting elements.
Yeah, so Jeff, you talked about the quite a lot of benefits and savings there. How do you go about working out what a customer site might be able to generate in terms of and carbon savings.
Yeah, that's a very good point, David. I mean, we've developed a number of tools actually for that. And in the first place, we start to talk to customers and they say, well, I don't really know exactly what the demand on the chillers is, but we've got, we can give you some indication of the annual energy consumption, annual electricity energy consumption. And at the same time, give an indication of what we believe the proportion of the chiller load is in that annual. And so we've got some models which from that can basically predict what the value will be of the load shifting of chiller optimization. Indeed, if there's any, I haven't mentioned this, but if there is any particular heat demand on the site, then the system also recovers the heat from the charger, and that can also provide quite considerable benefits. So basically, we have a simple tool which will look at an annual energy bill and a proportion of the chiller from that. Quickly thereafter, if a customer is interested, we would request an annual set of half-hourly energy data. Or I think in the US it's typically hourly, but basically a breakdown of the time of use profile of that electricity use. Ideally, that would come along with the BMS data, which shows what the chiller demand has been in that same period. And from that, we can obviously be much more accurate about sizing the appropriate EnergiVault store and what value that delivers, both in terms of those elements I just mentioned. So the load shifting, the potential aggregation and demand response, the chiller optimization, any heat recovery, and indeed any solar or other renewable integration. So we have a method of producing quite a detailed business case effectively once we have that data.
And this slide up on the screen, Jeff, this is what really we're using to suck in all the variables.
Yeah, this actually is just the first way of approaching this. So it's effectively with annual data. So this is not obviously looking at half-hourly data, but it is taking a view based on the annual energy demand and the proportion of that being chillers, and taking other energy related data, the pricing data, it shows at the bottom there the electricity tariff, and it effectively gives a view of what that tariff will be based on the combination of GEOS and the location. So we can produce quite a reasonable estimate of benefits based simply on annual energy data. Sorry, non-half-hourly energy data, but we can be much more accurate and illustrate that in quite a lot of detail, which customers will like to see before making such a commitment. So yeah, we have quite a number of tools that help us to illustrate the value.
And how does that value transcribe into payback, and pound notes rather than principles?
Well, again, it does depend on the application, as I mentioned, but on the specific site situation, operating parameters, energy costs, and so on. But typically, we would find for a system which doesn't use the heat recovery and is primarily about energy management, chiller optimization, load shifting, and so on, we'd typically be looking at sort of a 3-year or so payback. If you're recovering the heat, you could actually be talking considerably less than that, and maybe less than 2 years. In some cases, we've seen 1.5 years. So yeah, this table on the slide on the screen in front of us is assuming a 365 day year operation, 16 hours a day, so 2 shifts effectively in a factory with a considerable cooling demand, well in excess of an EnergiVault. So this is providing support cooling in a range of ways. The savings here, as this suggests, are sort of tiered really, based on what we might consider to be sort of the primary or base application for an EnergiVault, which is where you're doing time of use load shifting and you're optimizing the existing chillers. So you're minimizing chillers on part load. You're using the energy store to avoid high cost periods of energy or energy costs like GEOS. The second tier there, again, adding in the heat recovery to one, you start to see quite a considerable set of other benefits. and you can recover heat off the higher temperature part of the charger system, the de-superheater effectively, where you can basically store probably 70 degrees or so of water. Typically, that's at the rate of the mechanical work on the compressor, so you're able to store a reasonable amount of heat. And similarly, if you avoid using a cooling tower, you can store the condensing heat at a lower grade of heat. So that gives you quite a considerable additional benefit. If you want to use the heat off the system, increases the overall efficiency considerably. But the bottom line there, row 3, shows almost double the value in this particular scenario. Again, I have to be clear, this is a particular scenario, case study, if you will. Each one is slightly different, but where you're utilizing on-site renewables as well, then clearly there's significant advantage both in terms of carbon reduction and energy reduction. And I should say, although it only looks like a relatively small increase in percentage, we're taking account of the wider loads by putting those efficiency figures in as percentages. So yeah, as I've said a few times, it depends on the application. It depends on the customer's duty cycle, their energy, commercial energy bills. But broadly speaking, we'd expect between sort of 2 and 5 years payback on a system, by the way, that is designed to last about 20 years. So there is a considerable lifetime benefit. One thing that actually not mentioned, companies and people do say, well, how does it compare to to lithium-ion batteries? And it's a really good question. And why would you store energy in cold energy? Well, we've done the numbers on this, and we've done quite a bit of work, and one of our colleagues has done quite a lot of work with grid storage, battery grid storage. So we do have quite a handle on the costs associated with it. We also have a good handle on how lithium-ion batteries perform. Most people know they, over a period of 10 years, the battery capacity will degrade to about 70% of its starting position. The turnaround efficiency on lithium-ion batteries is generally sort of 85%, whereas there's no degradation and greater than 95% turnaround efficiency on EnergiVault. You're not having to change or replace the lithium-ion batteries every 10 years. You're not limited by the number of cycles that you can deliver. And overall, based on even the latest figures we've got from battery storage costs, you're at least 40% cheaper on a lifetime basis, and around about 20% cheaper on first costs. So if you have a large chiller load, then store energy and manage that chiller load and energy and carbon with cold storage, not lithium ion.
Okay, thanks, Jeff. I'm just conscious of the time. We're coming towards the end of the 45 minutes that we've planned for. If there are any questions from the audience, if you could perhaps put those through on the Q&A facility. But just while we're waiting for any of those that might come through, Jeff, perhaps you can just wrap up with you. We've covered a lot of ground there. Perhaps just give us a 60-second wrap up of EnergiVault.
Okay, well, we started off by saying EnergiVault allows flexibility, and I think that's a key thing here. Most chiller systems, and we've looked at the numbers on this. There are probably in excess of 10 million chillers out there worldwide, and most of them will not have any flexible energy storage associated with them. So the market for and the potential for adding flexibility to existing chillers as well as new builds is immense. Everybody's trying to get to net zero. If companies have renewables on site, optimizing those, optimizing the energy usage both in carbon and pounds terms has been difficult with chiller systems. EnergiVault basically allows you to provide that flexibility both behind the meter for the site's operation and efficiency, and also to the advantage of the network, which you can be paid for on the other side of the meter. So that and the technology probably also should be mentioned. The charger and the means by which we create and crystallize the fluid is actually a technology which has been used by the founder previously for crystallizing seawater for trawlers. So this technology is not high risk. In fact, the technology risk is very low, and we've demonstrated that with the system that we've got. So we're very confident that the potential for adding thermal energy storage to chilled water circuits really can help many companies move towards their net zero goals. And I think, we'd be obviously very keen to talk to anybody who's on this webinar. We know this is going to be distributed more widely, and hopefully over the course of the next few months engage with some of those companies to help them on their journey towards net zero, at the same time reducing their energy costs. So I think energy storage has been around a long time. EnergiVault allows customers now to do things differently and provides fundamentally that flexibility that hasn't been there previously for chilled water systems.
Okay, great. Thanks, Jeff. Absent any questions, I think we'll wrap up the webinar there. So it's 1:45 now, so pretty much bang on time. Apologies, everybody, for my technology failure, my camera ceasing operations halfway through, but I hope you found that useful. Thank you for coming and listening to the webinar. And if there are any questions after the event, feel free to get in touch with either Jeff or myself or Bob as well. Again, apologies again that Bob couldn't make it. So thanks, everybody. We'll dial off now. Bye.
Thank you.